Alright, so good afternoon to everyone. A very good afternoon to all of you, my dear students. A very good afternoon to all of you. So, guys, in this session, we are going to complete the properties of solids. Okay, so guys, my name is Dr. Shankar Sir. I am your physics educator, and in today's session, I'll be telling you about the remaining part of the properties of solids. Okay, so previously in the properties of solid, okay, so in the previous sessions, what we have done, so in the last session, what we have done, so we have spoken about the strain energy. So till now what we have done, so we have dealt with the Hooke's law previously, okay, so we have dealt with the Hooke's law already. We have dealt with the Hooke's law, we have dealt with the self-weight case, right? We have dealt with the tapered bar, right? We have dealt with the thermal stresses, right? So all this thing you can see in the previous videos or previous sessions of this topic, okay? Right? And also we have done bars in series, okay? We have done bars in series, right? We have done bars in parallel, right? So all this we have done previously, Vida. Okay, and also we have done strain energy, right? Strain energy, we have learned to calculate the strain energy, and also we have done, the stress strain curve, stress strain curve. So till this session, all these topics that belongs to the properties of solid are completed. Okay, so in this session, what we are going to do, so in this session, we'll be talking about the shear stresses and shear strain. Okay, so in this session, I'll be completing this particular topic. Okay, so shear stresses. So see, from the Hooke's law, so we understand from the Hooke's law, see, what is the Hooke's law, guys? So Hooke's law is what is the Hooke's law? So Hooke's law is corresponding stress is proportional to corresponding strain. Corresponding stress is proportional to corresponding strain within the limit of proportionality. Okay, so remember that Hooke's law is valid within the limit of proportionality. Now from the Hooke's law, we have related the normal stress and the normal strain, that is the longitudinal strain, right? Okay. So now from the Hooke's law, we can also say that shear stress is proportional to shear strain, that is tau is proportional to shear strain. So we'll be representing the shear strain like this. Okay. Okay, so this we can write. So when we let go of the sign of the proportionality, we are well aware that there will be some proportionality constant. So that proportionality constant we call it as G. And what is the G? So G is your shear modulus. Okay, what we call it? We call it shear modulus, or we call it modulus of rigidity, and we call it modulus of rigidity. So when we related the normal stress and the normal strain from the Hooke's law, we come up with another constant, that is the Young's modulus, right? Now when we are relating the shear stress and the shear strain, what is going to happen? We are going to have the modulus of rigidity or the shear modulus. Okay, okay. Now see, this is a strain. Now please understand this. This is the strain, so it is dimensionless. Okay, What is it? It is the shear strain. Okay, and we very well aware that strain is a dimensionless physical quantity. Okay, and this tau, it is the shear stress. Okay, it is the shear stress. So what is the unit of stress, sir? This is megapascal or gigapascal or Newton per meter square, whatever you say. Okay, Newton per meter square. So what will be the unit to the G? What will be the unit to the G? It will be Newton per meter square. Okay, Newton per meter square. Okay, 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 okay. So what will be the unit of this shear modulus? The unit of the shear modulus will be Newton per meter square. Right? Now see, what is this shear stress? So please understand this. So see, till now on a body, okay, till now on a body, so we have seen this previously. So on a body like this, okay. So now when the load is applied like this, when the load is applied like this, so what happens when the load is applied like this? It is going to have, yeah, sorry. So now see what happens. So when we apply the load like this, what happens? So it is going to get elongated or deformed like this. So in this part of the physics, basically we deal with the deformation. Whenever a load is applied and it affects the body with some deformation or deflection, then in that case this part of the physics works, right? So when we are applying a load like this, when we are applying a load like this, when we are applying the load like this, the body deforms this way. The body deforms this way, right? Yeah, hello Pradipta. How are you doing with that? So now in this case, the body deforms this way, right? Okay. So in this case, we applied the Hooke's law. We have seen that the stress is proportional to strain, and this formula comes up. Now, what is the shear stress, and in what condition our body will be subjected to the shearing or the shear stress, right? So see what is going to happen. Now please understand this. So we have analyzed this completely. We have seen all the possible cases in it and we have understood it completely. Now see, if a body is somewhat like this, if a body is somewhat like this, okay, if a body is somewhat like this, now in this body what is going to happen? Now if I apply the load like this, Okay, let's say this is F. Now, if I apply the load like this, what is going to happen, guys? So, in this case, what is going to happen? So, this is going to be deformed somewhat like this. This is going to be deformed somewhat like this, right? This is going to deform somewhat like this. That means it is going to deform with some angle, that is, we call it as the gamma. And this is nothing but your shear strain, right? So when we are applying the force on a body like this, if it is fixed in the bottom, and if we apply the force somewhat like this, so now in this case, what is going to happen? It is going to have a change in dimension or change in shape somewhat like this. Okay. So now see, what is the shear stress? I want to see, have it demonstrated. Now see, this is somewhat like this. Okay, please see. Okay, this is somewhat like this. Now see, when I am applying the shear force, see, this is a body like this. Okay, this is a body. So this is a hollow, just to demonstrate the same thing to you. So see, when you will be applying the force parallel to the surface. Okay, so parallel to the surface, right? So see how it is going to have the change in the shape. So it is changing like this. The shape changes like this, isn't it? So it is going to see, now if you observe, there is some angle it is making like this, right? So when you are applying the force, it is going to be the angle like this. So some angle will be there. Okay. Okay. So that is why when a body is subjected to shear, it deforms. The change of shape happens like this. Okay. The change of shape happens to be like this, and this is L, and this is delta. This is delta. Okay. Okay, now see what is going to happen. So if I write here, now see, a string is changing dimension upon the original dimension, right? Now see, the shear strain is slightly different. Okay, it is slightly different. Its formula is slightly different. See, now what is this gamma? So can I write tan gamma is equal to delta upon L using the simple trigonometry? Tan gamma is equal to delta upon L, right beta? Now from here, now since the gamma is very small, can we write tan gamma is equal to gamma only? So this will become delta by L. So this is what you know as your shear strain. Okay, shear strain. And sometimes it is also known as the shear angle. What is it? The shear angle, right? Okay, so delta by L will become your what? It will become your shear strain. Okay, it will become your shear strain. So I hope this is clear to everyone. Okay, so when the force, so when the shear will happen, now please observe this. So see, when we are talking like this, see, this is the face, right? And if I try to understand this concept in 3 dimension, it is somewhat like this, right? This body is somewhat like this. This is fixed here, right? Now, when we are applying the force here like this, now you see it is causing the shear. Okay, why it is shear force? This force we call it as shear force. This has the effect of the shearing. Okay, so what do we mean by shearing and how we identify the shear? So basically, shear force is something which is the plane, parallel to the plane of cross section. It is parallel to the plane of cross section, right? Okay, so this is the shear force which is parallel to the plane of cross section. Now if I see this P, please understand this. So now when you see this P, so this P happened to be normal force. Why it is called as normal force? So normal to what? Shear means parallel. Sometimes it is also known as tangential force, right? Sometimes people call it tangential force also, right? So whenever we are writing the shear force, tangential force, or anything like that, basically we are using this word shear or parallel or normal or tangential. So we are taking it with respect to the cross section, the plane of the cross section. So this is the plane of the cross section. This is the plane of the cross section, right? Okay, so this is what we call as the cross section. This is cross and this is section. Okay, remember that. Okay, so when we are saying that, so this is your plane of cross section, which you call as, this is what we call as the plane of cross section. Understood, beta? Please answer me. I hope this is fine to everyone. Right. Okay, so whenever we are referring to whenever we are seeing a force, we are seeing the force with reference to, we are seeing the force beta with reference to the plane of cross section, and according to the plane of cross section, or with reference to the plane of cross section, the force can be called as the normal or the shear. Understood beta? I hope it is fine to everyone. Yeah. Please answer me, the live students. Please answer me, guys. Yes or no? Oh, okay. Okay, so Cakewalk, welcome to the session. So, beta, we are talking about the shear stress today. Okay, okay. Now, how can we relate? Now, how can we relate the stress and the shear strain? So, see, how can we relate the shear stress and shear strain? So, see, by the Hooke's law, we can write that the shear stress is proportional to the shear strain. So shear stress is proportional to the shear strain. That means when we let go of the sign of the proportionality, we get tau is equal to G times gamma. Okay, what we get? We get tau is equal to G times gamma. Right? So what is the shear stress? This is force upon area. What area we must take? So we must take the area of the cross section is equal to G times gamma. Right? So what is this gamma? This is delta by L. So delta by L. Okay. Okay. So L is what? L is this height. Right? So this is what we are talking about, this L. You can call it the height of it also. Right? So from here, whatever missing data is there, you can try to figure it out. Okay? Okay? Did you get it or not? Please answer me. Please answer me. बोलिए. Okay. You want me to repeat? Okay, no problem. I'll just give you a flashback. Okay. So see what we were talking about in this session. So we started with this. So see, in the properties of solid till now in the previous sessions we have completed all these things. Okay. What we have completed, sir? We have completed the Hooke's law. We have completed the self-weight. We have completed the tapered bar. We have completed the thermal stresses. We have completed the bars in series. We have completed bars in parallel. We have completed the strain energy, and we have completed the stress strain curve. Okay. So if you want to learn all these topics, so you can refer to the videos on this channel. Okay. So you will be seeing that we have completed all these things, right? Previously, right? Now see, what is going to be the shear stress? What is going to be the shear stress? So shear stress is, so we are talking about the shear stresses. So Hooke's law you must be aware of. Are you or aren't you? Yes, sir. We are aware of the Hooke's law. What does the Hooke's law say? It says corresponding stress is proportional to corresponding strain within the limit of proportionality. Remember, the Hooke's law is valid within the limit of proportionality. Okay. So now from Hooke's law we can relate that the shear stress is proportional to shear strain. That means tau is equal to tau is proportional to tau is the representation of shear stress, right? Though it can be represented in any way. See, shear, normal, all these shows the tendency of the force. All this shows the tendency of the force in which the force is acting with respect to the cross section, right? With respect to the cross section, how the force is acting, that is what we meant by the shear, or normal in that case. So how we understood the shear? So this is what we have dealt already. Are you getting my point, Cakewalk? So what we have dealt already is this much. Okay, so if on a body this load is applied like this, okay, so this load is like what? So see, if you try to visualize this in 3 dimension, it is going to be somewhat like this, right? It would seems to be somewhat like this. Yeah, it seems to be somewhat like this. Okay, so when a body is subjected to a load like this, so this is now in this case, this is the cross section. Okay, now you see this load is normal, that is perpendicular to this cross section, so we call it the normal load. And in normal load, we further call it the axial load, right? Now, due to this load, a body will have the tendency to deform like this. Okay, it will have some elongation in its length. It will have some elongation in its length, right? Like this. Okay, okay. Now, what is the shear load? So, see, when on a body, when you are applying the force parallel to the cross section, like in this case, if I apply the load like this, in this case, if I apply the load like this, the W like this, so this is going to become the shear. Okay. So when we say the shear, so its other name is tangential. Okay. So the shear force is the force which is parallel to the plane of cross section. Okay. So if on a body the force is applied in a way that it becomes parallel to the surface of the cross section or plane of the cross section, we call it the shear force, right? Like if we are having a body, okay, and it is fixed in the bottom, and when we are applying the force like this on the surface, it is going to show this tendency. So this I wanted to explain with this demonstration. So see, this is a body now somewhat looking like this. So when we are applying the force like this, see, we are applying the force like this. So when we are applying the force like this, so if I apply, so it will become like this, right? It goes like this. So it will have the change of shape will happen to be in some sort of a angle, isn't it? It will be in some sort of a angle, right? Okay, so it will become gamma, right? It will show you an angle gamma, and basically if you see the dimension, so there will be some delta. Okay, so delta will be displaced, this body will be displaced, or the surface will be displaced somewhat like this. The surface is going to displace somewhat like this. Are you getting my point, beta? Please answer me. Cake? Yes or no? Yeah, are you getting it? Yes, sir. We are getting it only. Okay, wonderful. Now, if this force is applied like this, so the surface will show some deflection, some displacement. And when we talk about the shear strain, so see, if you apply a little trigonometry here, you will see that this is the angle and this is the perpendicular, this is the base. So we know that the tan gamma is perpendicular upon base, that is delta by L. And now for small angles, right, small angles, I hope we are aware that for small angles, the tan gamma will become gamma itself. So gamma will become delta by L. Okay, okay. So same thing I was trying to explain. Now from Hooke's law, we know that tau is equal to G times gamma. So F by A will be G delta by L. Understood? Yeah, please answer me. So now let's solve a few questions so as to better understand this concept. Okay, so let's try this one. Okay, so let's try this one. I'm very sure we can do. So in this case, you have to find the tau, that is the shear stress, and you need to find the gamma. Please go for it, guys. I'm very sure we can do. Please try. Please try it. I'm very sure we can do it. Please go for it. Please go for it. Please attempt. Please attempt. Please do. Please tell me when it is done. Please tell me guys when it is done. All the live students. Please try to do it. So, Cakewalk, you have answered something. What about you, Pradipta? Okay, I'll try. So, it says a block of 100 mm cross 100 mm base and 10 mm height. So, let's try to figure it out. So, the base is 100 mm cross 100 mm. So, the base is 100 cross 100. So, basically, what happens? See, so this is 100 and this is also, sir, but they say base, so it doesn't matter, beta. Okay, because see, if base is also, there will be some reaction at the base, and the reaction will be same as the force applied. Okay, so now when we apply a tangential force of 10 kilonewton to the upper edge, now if I apply the tangential force of 10 kilonewton to the upper edge, it is displaced 1 mm relative to the lower face. Okay, so 1 mm relative to the lower face, that is what happens, and the height is 10 mm, right? The height is 10 mm. So how it will become? See, So this is going to be like this. This is going to be like this, right? Now they say that this is going to be displaced 1 mm, okay, 1 mm. So we have to firstly find the shear stress and shear strain. So what is the shear stress, sir? It is force upon area. So what is this force? This is 10 kilonewton, that is 10 into 10 to the power 3 upon area, that is 100 into 100. So basically this is 1 megapascal. Okay, this is 1 megapascal and not a cakewalk. So I assume you are trying to answer me that only, na? Yeah. Okay. Now what is the shear strain? So shear strain is given by delta by L. So delta is 1 upon L, that is 10. Okay, so your strain will become 1 by 10. Always take care of the units, that in strain you are putting the same unit there also. Right, now if I ask you the G, so we know tau is equal to G times gamma. So if the shear modulus is asked, so what is the shear modulus? So this is going to be tau, that is 1 megapascal upon 1 by 10, because gamma is 1 by 10. So this will become 10 megapascal. It will become 10 megapascal. So everything you could find from here, right? Everything you could have found from here, right? Now let's try one more question. Okay. Let's try this one. I'm very sure we can do. Please go for it. Let's try to do this one. I'm very sure we can do. See, in physics, it is very important that we solve many questions. Please do. Very simple question. Let's try it. Let's try it. Oh. Yeah, sorry, it seems like you couldn't hear me. Okay. So now I'll just do it again. So it says a square lead slab of side 50 centimeter and thickness 10 centimeter is subjected to a shearing force of 9 into 10 to the power 4 Newton and the lower edge is riveted to the floor. So when they say lower edge is riveted to the floor, it means that the lower edge was fixed. Yeah, Krishna, Joseph, I just have sorted this out. Now I hope you can hear me. Can you? Krishma. I'm really sorry. There was some technical issue, so that is why there was no sound. Yeah. Now can you hear me right? So, beta, we are talking about the shear stresses today. My name is Dr. Shankar Sir, and I'm your physics educator. Yeah. So, can you hear me now, all of you? I hope you can hear me now. Okay. So it says a square lead slab. So I'll just check once. Yeah. Now the sound is fine. Actually, I have my mobile. I see your chairs in my mobile actually, but I have to keep it sound, mute so that otherwise you will see this. You will hear the sound of my mobile, right? Okay. Sometimes it happens. Okay, I'm sorry. So now we say the square lead slab of side 50 centimeter thickness 10 centimeter is subjected to a shearing force like this. The lower edge is riveted to the floor. How much? How much will the upper edge be displaced? So basically what is asked in the question? So we are asked about this delta, right? We are asked about this delta, right? So I'll just make it again. So see, it says that it is riveted at the ground. So riveted at the ground, that means it is fixed, right? And now this is a square. So please see the dimension, that 50, square of 50. So this is 50, this is 50, and the thickness is 10, right? The thickness is 10. Sir, how you realize that the thickness is will be like this? So see, because they say that the force is applied on the narrow face, right? So what would be the narrow face? The narrow face obviously would be the one having the 10 centimeters. So this is going to be the narrow face, right? Now the force is like this. So F is, we are having the force that is 9 into 10 to the power 4 Newton, right? Okay, now due to this will have some change of shape like this. So what is asked to us? So we are required to find this delta, right? We are required to find this delta. So what is given in the question? Shear modulus is given. So now we can relate that shear stress is proportional to the shear strain. So tau is equal to G times the strain. So what is this tau? So this is force upon area. Area is what? Area is 50 into 10. So answer is in mm. So let's convert in mm only. So this is 50 centimeter into 10 centimeter. That is 500 mm into 100 mm is equal to G. So G is, so actually this is 10 to the power 9, not this, right? Not this minus. Shear modulus can't be this less, right? So G is going to become 5.6 into 10 to the power 9 Newton per meter square, but we want answer in mm. So let's change this into mm. So we'll be getting 5.6 into 10 to the power 3, and this gamma is going to be delta upon L. L is 500. L is 500. So from here we can have these two cancel out, okay, and we will be getting how much? We will be getting zero point 0.9 divided by 5.6, that is 0.16, okay. Okay, okay, so see, if you see the option, Okay, no, you need not to calculate even, because see, we are getting here zero point 0.9. See how you solve this question. So when you calculate it, you will get 0.9 divided by 5.6, isn't it? Okay, are we getting that? Right? Zero point 0.9 divided by 5.6, and the unit is in mm. So obviously what we are going to get, beta, obviously we are going to get something which is less than 1. This is in decimal. Okay, so it must be 0.16. I hope this is fine to you, beta. Yeah, how we have solved this question, is that clear to you or not? Please answer me. So let's try one more question. Okay, let's try this one. I'm very sure we can do. Come on, all of you. Please do. Please do. Hello, Saikat. Welcome to the session, beta. My name is Dr. Shankar Sir, and in today's session, we are dealing with the shear stresses. Okay, properties of solid. I hope your preparation is going fine. Can you try this question? Please solve this. Any answers? It's a very simple question. Please try to deal with it. Please try answering it. Saikat, Pradipta, Cake. Cake work seems incorrect. What is your answer, Krishma and Saikat? Can you please answer it? So if any new students, please do subscribe the channel as well. Right. So okay, let me do it. So it says that the cube is fixed. A cube of side 1 meter is fixed at the lower end. And is acted upon by a tangential force F on its upper surface. If shearing strain is 10 to the power minus 2 due to force F, find the distance that the upper face is sheared with respect to the lower face. Okay, so how we can deal with it? Oh, Prajakta, you are asking me to wait. Okay, I'll wait. 2 more minutes. Please attempt it. What about the rest of you, beta? What about the rest of you? Saikat seems to be incorrect. So see, it says a cube of side 1 meter is fixed at the lower face is acted upon by a tangential force on its upper surface. So let's try to figure it out. So we are having a cube. So cube is something which has all the sides of equal dimension. So this is 1 meter. This is 1 meter, right? Right, and we'll be having a tangential force F acting like this. Yes, I'm doing it. So now this is the force, tangential force acting like this on the upper surface. So shear strain is 10 to the power minus 2. So see, this is going to have a change of shape somewhat like this. So let's suppose this is delta. Okay, so they have given you the shear strain. So shear strain is what, beta? It is delta upon L. This is L. Right, so shear strain they have given, that is 10 to the power minus 2, and they are asking you find the distance that the upper face is sheared with respect to the lower face. So this is delta and this is 1. So delta will be 10 to the power minus 2 meter right away, isn't it? Cycle. No, it is not 10 to the power minus 4. Are you getting my point? Right? Please answer me, beta. बोलिए. Is it clear? What about you, Pradipta? बताइए बेटा, क्लियर है? बोलिए. बोलिए. Wonderful. And what about you, Cakewalk? Okay, I hope it is fine to everyone. Now let's do one more question. Second, did you understand this concept? Properties of solid, right? Okay, wonderful. So let's try one last. Okay, so that we will be more comfortable with this topic. Very easy, no? And they can ask you the shear angle also. See, shear angle, shear strain are more or less the same thing. Okay. Come, let's try this one. I'm very sure we can do. Please go ahead. Second, I think this is the first time you are on this channel, na? So my name is Dr. Shankar Sir. I'll just introduce myself to you. So this is my brief introduction. I have done Masters and PhD from Indian Institute of Technology, Roorkee. and I have been teaching this physics from some 10 years. Okay, just a brief introduction. Okay, so now we can try this question. So on the channel we have done so what we are doing, we are trying to uh, help you guys in your NEET preparation. So in that order, I have completed on this channel in physics, units and measurement. We have completed motion in a straight line, motion in a plane, and also we have completed the vectors, basic mathematics, and this is the last session. The previous question, do you want me to solve? I'll just explain you the whole concept. See, please understand this. So see, this is the first chapter of your 11th part 2. Okay. Now see, when cycle, so there is something in physics that is called the force. Okay. Now this force, when it is act on some body, it has the nature to do something with the body. Are you getting my point? What I'm trying to tell you, right? Yeah, I'm going to solve it only. So you tell me that whenever a force is acting on a body, basically force is something which will do something to somebody. Okay, when it is acted upon on when it is acting on something, it will definitely have some effect. Like for example, let's suppose we are having a body like this, right? Now on this body, if I apply a force like F, okay, so if I apply the force like this, so it is going to have some displacement. Okay, a body will have, so body will obviously move in the direction of the force, right? It happens, right? So basically in this part, okay, so this is what we call as the, we have seen in the Newton's law of motion, kinetics, right? In all those parts we talk about this. Okay, so when a force is applied on a body and it displaces, when displacement happens, we talk about velocity, then we talk about acceleration, and when the body have the acceleration, inertia force comes into picture, Newton's second law start coming into place, like F is equal to ma and everything like that, right? This happens or not? Please answer me. Yes, sir, it does happen, right? Now, in this part of physics, what we are talking about right now, in this, so if I am applying the force on something, if I am applying the force on a body, see, cycle. I just try to explain that what we are doing. Now, if I apply some force on the body and if I displace, if I fix it from one side, so it is going to show some deformation like this. Okay, so you know it. Wonderful, Bila. So now in this part of physics, we talk about the displacement, right? Now, if the force on a body is applied like this, see, if a force on the body is applied like this, okay? So now it is going to change of shape like this. So basically in this part of physics, we talk about the change of the shape. Very good afternoon, Harsha. Sorry, in the last night, some, power cut happened. That is why I couldn't come live at 8. I'm really sorry about it. I saw in the morning your message. Okay. Okay. So second, this happens. So see, what is the strain? Right? So what is the shear strain? We are talking about the shear strain. So this is the shear strain, and this is delta, that is the displacement of the upper face, and this is L. Okay, so the shear strain is delta upon L. Are you getting my point? This is the shear strain. And if we apply the Hooke's law, so we say tau is equal to, that is the shear stress is equal to G into shear strain. So this is the brief introduction, right? Now let's come to this question. Harsha, do you know about this? Have you gone through this chapter? Do you know, like in this properties of solid, what do we talk about? Yeah, please answer me. Yeah. So now let's solve this question. Okay, cakewalk. Let's see. So now it says one of the square faces. So I'll just copy it here. Right. Now see, one of the square face of metal slab of side 50 centimeter and thickness 20 centimeter is rigidly fixed on the horizontal surface if a tangential force is applied. If a tangential force is applied, so see, when we are talking about the slab, see what will happen to the slab. So see, it is somewhat like this. Okay, this is somewhat like this. So see, right, this is your slab. Okay, you got it. Wonderful. So this is the slab, right? Now, if this is the slab beta, so what should be the, so now see, please understand this. So one of the square faces of the slab having side 10 centimeter and it is fixed on the horizontal surface. So that means this is 50 and this is also 50, isn't it? This is also 50. See, sometimes we get confused. In this only there is one twist, that which dimension will be there. So this is 50, this is 50, and the thickness is 20. So thickness is 20. So how we understand this? So because it says that it is fixed on the horizontal surface and the surface is square, isn't it? The surface is square, right? So now when we are fixing it from the horizontal surface, this is 50, this is 50, and the tangential force of 30 Newton is applied. Okay, so we are applying the force of 30 Newton and we are asked about the displacement of the top surface. That means we need to find this delta. So let's see this another orientation. In two dimension if I see, so I'll have to see this, right? I'll have to see this. So this is going to be the delta. This is going to be the delta and this is 20. Okay, so ultimately we have to find this delta. Okay, so now we can apply the Hooke's law. So shear stress is G times shear strain. Yeah, we are just trying to complete it. So the answer is yeah, cycle. Very good. Harsha, what is your answer? Pripta. Okay. So now the shear stress is what, sir? It is force upon area, that is 30 upon, now see, we have to find the displacement of the top face, right? So see, the displacement of the top face. So nothing is mentioned actually in this question. They should have mentioned the unit also, because see, so this is in meter. Oh, so it is written in meter. So we have to find in meter, right? So now this is 30 upon now 50 cross 50. So can we write it as 0.5 into 0.5? Because we have to ultimately find answer in meter. Now what is G? G is 4 into 10 to the power 10. And what is this gamma? This is delta upon 0.2. Delta upon 0.2. So from here when we are solving, we are getting delta is equal to 6 into 10 to the power minus 10 meter, right? Right? Is it fine to everyone? Please answer me. So this is how we deal with the shear stresses and the questions with the shear stress. Understood? Any issues? Please answer me. Right? Okay, clear. Now see one more thing. So if you remember about the strain energy, so see what we have found the strain energy. So strain energy per unit volume in the case of the load is normal. So when the load is normal, if you have gone through the previous sessions, you must be knowing that strain energy per unit volume is given by sigma square by 2e, isn't it? Okay. Now in the case, see, try to understand the analogy. So strain energy due to shear load. So strain energy due to shear load, what it is going to be. So due to shear load, see, it is in the same analogy, in the same line, it will just become tau square by 2g. Okay, tau square by 2g. Is it fine, beta? So if at all they ask you to find the strain energy when a body is subjected to the shear load, will you be able to do it? Yes or no? Please answer me. Bole. So can I say that the shear stress thing is also sorted? Yeah? Please answer me. Bole. Wonderful. Now let's move ahead. Yeah, is it clear to you also? Saikat, Pradipta? Wonderful. Now, let's proceed. So now we have dealt with the normal stress, normal strain, right? Normal stress and normal strain are dealt, right? Normal stress and normal strain. Okay, normal strain. So this is dealt, right? Now shear stress and shear strain is also dealt, and shear strain. So we just now have dealt with it also. This is also done. Okay, now we have one volumetric stress. We have one volumetric stress and volumetric strain. Volumetric stress and volumetric strain. So now let's deal with this also. So this is also the part of this particular chapter that we deal with, this volumetric stress and volumetric strain. So now, as we know, so let me do one thing. Let me just copy this thing. So we know the Hooke's law, right? Okay. So basically, Hooke's law helps you relating the shear stress with shear strain, the normal stress with normal strain, and similarly the volumetric stress with the volumetric strain. Okay, I'll just, yeah. Now please try to understand this. So we know the Hooke's law. Hooke's law is corresponding stress is proportional to corresponding strain. Corresponding stress is proportional to corresponding strain. Now corresponding stress being proportional to corresponding strain, so in this volumetric stress is proportional to volumetric strain. Volumetric stress is proportional to what, beta? It is proportional to the volumetric strain. So in this case, when I let go of the sign of the proportionality, I'll get something as the bulk modulus, right? So this bulk modulus you see in the fluid also, no? Okay, because see, this volumetric stress has something to be doing, it has something to do with the fluids also, right? So see what happens here. So what is this K? So K is the bulk modulus. Okay, K is the bulk modulus, right? K is what? K is the bulk modulus, and basically this K we can write as the volumetric stress upon the volumetric strain. Okay. Now, so what is this volumetric stress and volumetric strain? Now, please understand this. So, where it basically find its use, and when some sort of a stress, we can call it as a volumetric stress. So, let's suppose we have some body, and this body is inside a static fluid. Okay, this is some sort of a liquid. Okay, it is, it has liquid around it. Okay, it has liquid around it. Now see, in a static fluid, I hope we understand this. I hope we understand this. That, sir, in a static fluid will be giving the pressure normal to each of the point of this surface, and all this pressure, okay, all this pressure is going to be equal, isn't it? All this pressure is going to be what? All this pressure is going to be equal, isn't it? Okay, okay. So see, in such conditions, okay, whenever a body is subjected to equal forces on all the surfaces, okay, okay, then we can call it the volumetric stress, and that is why sometimes it is also known as the hydrostatic stress. Hydrostatic stress, and this hydrostatic stress, it is also known as the volumetric stress. So see, when in a three-dimensional body, if the stress on all the perpendicular faces is same only, then we call that then we say that the body is subjected to the volumetric stress, and due to this it will have some strain, some change in its volume, and we call it the volumetric strain. We call it the volumetric strain. Are you getting my point, beta? and this is given by change in volume upon original volume. This will be given as change in volume upon original volume. I hope it is fine to everyone. Yeah, please answer me. Right. Okay, so whenever a body is subjected to hydrostatic pressure on its surface, it is going to develop some volumetric strain, that is change in volume upon the original volume. Understood, beta? Please answer me. Please answer me. Yeah? बोलिए. Right or wrong? Right. So let's do one question so that we understand it better. So see, just a simple formula. Just a simple formula. What happens? So volumetric stress is proportional to volumetric strain. So K times the volumetric strain. Okay. Okay. So basically, this volumetric strain is also the change in pressure. Okay. Divided by this volumetric strain, there's a change in volume upon original volume. Okay, and see, we apply one minus sign here. Why? Because we know that the pressure and volume have the opposite relationship, right? See, if we are increasing the pressure, the volume basically decreases. So volume and pressure basically have the opposite relation, right? So let's do one question so that we better understand. See, in physics, like more than theory, we must focus upon the question. With the help of question, we can even better understand the theory, right? So let's see how we can deal with this. Okay, let's try this one. So for new students, please do subscribe the channel. Yeah. Okay, let's try this one. So you have all the information of solving this question. Please go ahead. Please go ahead. Please try. I'm very sure we can do. So we have to find delta V by V. Please try doing it. We have to find delta V by V. Any answers? Any answers, guys? Wait, push. Oh. Can you give me some answer, beta? Anyone? Please do. Any answers? Very good, Harsha. So it says the average depth of Indian Ocean is about 3000 meter. Calculate the fractional compression delta V by V of water at the bottom of the ocean, given that the bulk modulus of the water. So bulk modulus is given. So see. So you must be aware of a formula P is equal to rho GH. Are you aware of it? P is equal to rho GH. I will see to it. Okay. P is equal to rho GH. So they are asking you in percentage only, na? So you need to multiply 100 to it, right? So you'll get 1.36%. So P is equal to rho GH. From the hydrostatic law, we get this, right? So rho of water, so they haven't given anything, so you can consider 1000. G is, you can consider 10, okay? So they have given it 10, and H is 3000, okay? So P you have, okay? So this is delta P basically, right? And we know that the volumetric stress is proportional to volumetric strain. So volumetric stress is how much? 1000 into 10 into 3000 divided by bulk modulus. What is the bulk modulus? There is 2.2 into 10 to the power 9. So from here we get the change in volume upon original volume, isn't it? So I guess when we are solving it, we are getting 1.36%. Is it fine, beta? Please answer me. Yeah? Please give me a yes or no. Please give me a yes or no. Right? Okay, so see, this is the simple way that how you can deal with it. have, okay, so sorted only, na? Yeah. So see, this is the, so I'll just check if we have any PYQs on this. Let me check. So now this chapter is finished. Okay, I have completed everything in this chapter of properties of solids. So the remaining of you, Saikat, Prita, Cakewalk, Harsha, I didn't get what you are trying to tell me. So when you are solving it, you are getting 1.36 into 10 to the power minus 2. But you see in the option they are asking you in percentage. So we have to write 1.36 because it is in the percentage. Right? Isn't it? And see which could be the option. Right? Okay. So 10 to the power minus 2 into 100 will become 1.36%. So I'll just see if we have any question of PYQ that we can do of this chapter. So this chapter is finished. Just give me a moment. I see if there is a good question. We can do it now, or otherwise we'll. Yeah, I got it now. Just a moment now. So we can try this one. So this is a PYQ. Let's try this. Let's try this. So when they say fractional decrease in something, that means they are asking you delta R by R. Are you getting my point? They are asking you delta R by R. And they are showing you the bulk modulus as B. And also one thing, if they ever ask you this compressibility, basically compressibility is 1 upon bulk modulus. Okay. So compressibility is reciprocal of the bulk modulus. Are you getting my point? Please do it. All the live students, please do subscribe the channel if you haven't yet. Whether you forgot. See, V is proportional to R cube. So when V is proportional to R cube, so delta V by V must be 3 times delta R by R, isn't it? Haven't we seen in the first chapter? Yesterday we were doing questions of it. You forgot? Yes or no? Please answer me. Okay, this is how it works now. Please answer me, madam. You have to find the fractional change. That means you have to find delta V by V. Okay, Pradipta, I have given some answer. Yeah, Pradipta, right only. Wonderful. Harsha, you also do Saikat. If you are here, you can also try. No problem, beta, no problem. Now you do. Now you please try to solve this question. Yes, I hope so. Hmm. Rishikesh, hello. How are you doing? So, are you trying this question, Rishikesh? Okay, let me do it. So it says the bulk modulus of a spherical object is B. So we know bulk modulus is, so pressure is there and it will be delta V by V with a minus sign, but we can ignore the minus here in the context of the question. Now delta V by V is 3 times delta R by R. So they are calling this bulk modulus as B, right? So in books normally they say B or sometimes they say K, it doesn't matter. So 3 delta R by R, so simply delta R by R is equal to P upon 3B, that is your P upon 3B, that is your C option. That is our C option. I hope it is fine to everyone, right? Yes or no? Please answer me. Yeah? Please answer me. Right. So, guys, with this, the properties of solid is completed. Okay. Properties of solid is done. It is completed now. And I hope you have understood this. So, on this channel, this is the 5th chapter I have just completed. Right, so see, this was the last video of this particular chapter. If you want to learn this chapter in much detail, you can refer to the previous videos of this particular chapter by the name of Properties of Solid, Hooke's Law, Strain Energy, Thermal Stresses. So I have dealt with everything very comprehensively, right? So later we will have a one-shot session of this complete chapter, okay, like we do for every chapter. This also I'll do, but I'll take some time for it, okay, so that if any students want to do some questions and everything, we can do that, okay. So guys, in this session, I'll keep it to this point, and in the upcoming session, again, like as usual, we'll be solving the questions live. Okay, so today we'll be trying to do the questions. So lastly, in the PYQ session, in the practice question sessions, we were done with the units and measurement, right? Now we are going to the next chapter, that is motion in a straight line. So we'll be solving PYQs and practice questions of the chapter of motion in a straight line. Okay, so that will be the upcoming session. So guys, if you haven't subscribed yet, please do subscribe. So I'll keep it to this session. Thank you very much. Have a good day, and we'll see you in the next session. Please do join the next session also.